Okay, we start up again. So now we have a solution, at least half of the solution, which looks very, very nice. But sadly, it is wrong. Not easy to see, especially here. We're sort of looking at the steady state in the end and so on. But you see it quite good if you remove the pause percentage here and step your way through it. Then you can see what's happening. First time step, second, third. Then you see down here at the symmetry line, he should be straight. Something is wrong here. He has gotten an angle. So this is going to be a very strange velocity profile, sort of a double, little erotic. So clearly something is wrong with my boundary conditions here. So how can we fix this one? Well, the way I did it now, I used the sort of the forward differencing to create the symmetry boundary condition, Neumann condition. But I put it up here. This is not correct. You have to do first the calculation, then afterwards you implement the boundary condition based on whatever velocities you have created. So I have to do it like this. Here I sort of update the entire field based on old values, and then I implement the boundary condition. Now you can see the difference. You run this one step by step. Then you see he's not zero here, it's straight line. So now he should be more correct. You see, straight line at the symmetry. Vertical there. So that's much more like it. Okay. Questions to that one? No, that's okay. So that means the version I just put out on the home page is wrong. So I'll update him later. Now let's solve these equations somewhat differently. We move these two, and I go back to the first one I had. So now we save him as Poiseuille pdepe. Pdepe, that's something we are going to look at now. Then I remove, what do we have here? Remove this one, well, not all of it. Just removing the ODE part. So here we have the initial solution, like that. Solve it using a built-in tool in Matlab. So you write duc pdepe, pdepe. Well, he's busy with something. What's he busy with? That was strange. Ah, he's frozen. Okay. Frozen Matlab. You try Ctrl+C in the command window, doesn't work. Then you use the task manager and kill him. And if that doesn't work, you have to restart the entire computer. That happens from time to time, actually. We got a warning, I think it was last time, the license is about to expire. I guess all of you got that. But it should automatically be renewed, so nobody had troubles, I hope. Yeah, good. Okay. Yeah, we are back where he was, and I write documentation pdepe. Here we go. If you have installed Matlab, including the partial differential equation toolbox, you'll have this function. Here you can actually solve nasty partial differential equations numerically. So Matlab has some built-in scripts that can solve these types of equation systems. How to use it? Not entirely easy. Here is the call. You get a solution from, and then you need actually 3 subfunctions. You have to provide him with a parameter m and mesh in the space and also in time. The coefficients here that's how you construct the equations you are looking at. For instance, the parameter m, he will determine if you want to have an x, 1 over x here, and then x here, or not, as an unknown. Of course, here you are talking radial, cylindrical or polar coordinate systems. There you have a lot of these 1 over r in the equation systems. Here I don't need him, so in my example I just put a 0 here. I don't want the function here. I want the derivative of a function, and here my function here is also then going to be a derivative. Then I have time derivative equals double derivative. That's what I need, and you can even have a source term if you like. And the source term, he does not necessarily, as you can see, be constant. He can be a function of the unknown or even the spatial derivative of the unknowns. And also the coefficient in front of the time derivative doesn't have to be a constant. So you can play around here with quite complex partial differential equations. How to use it? Well, we just find an example down here where they have solved here an equation looking very similar to what we are solving. So I just copy the recipe. Then I take everything here. Doesn't work. Here, now it works. Whoops, not all. Come on. Stupid machine. All the way there. I copy this one into a new file in Matlab. Not this one. I create another one and push it in here. Should be easier for you guys to see. So this is the example provided by the documentation. You create a distance and a time, and then you call the solution if you have now set up the proper subfunctions. We have a time space going now from -1 to 1. And we can have 20 of them. That's quite okay. Time goes from 0 to 2. That is 0 to 5. I think that is the different time levels actually. Yes. So we don't need that many. We can take from 0 to 3. And then take 6 of them. So here you specify where and when you want a solution. Then we have to address the coefficients in the equation first. This m set to be 0, that's quite okay. And then the first function, he decides how your equation actually looks like. So here you specify the coefficients, if you remember from the documentation. Coefficient c. In our example, he is just 1. The f function is derivative, then I get the double derivative on the other side, but I have a source term. He's not 0, he was 2. There I have my equation for the Poisson flow. Okay? Time derivative equals double derivative plus 2. Initial conditions, everything equal to 0. So that should be quite okay. It should actually be possible to do it like this. And then we have the boundary conditions. Boundary conditions, a little bit more tricky. You have a left and a right, and you have 2 coefficients you can play around with. If we go back to the documentation, the boundary conditions is, well, we have to go a little bit more up. Here was the original partial differential equation, initial state, and here you have the boundary conditions that you specify for the left boundary and the right boundary. So it can be a constant, or actually a function of both time and your unknown and the position, of course, plus another coefficient multiplied with a function that can include the derivative. So here you are talking Dirichlet condition versus Neumann condition. So what we want, that's Dirichlet. We have 0 in both ends. So I will write them on the form P left equals U left. Here it is written on the form that it must be 0 when it is fulfilled. So when I do it like this, the left coefficient for P is 0, Q is, is the velocity, and Q, that's 0, no derivative. Meaning he will set up as a boundary condition this one equal to 0. So that's only U left there. Q was 0, and here I then also need U right. And my Q there also is 0. Now we should have everything okay. And the solution, here you get a whole matrix, and the first component should be the solution only, and then here plotted with a surf. So let's run this one and see what happens. Yeah, give him the same name, but not that space. I want him in the same folder. Where is it? Here. There we go. So there we have sort of the final figure, only the final velocity profile, but they also provide with a surface plot giving you the different velocity profiles at the given time. So here you sort of also have the time development as well. So if you flip this one a little bit around, you should be able here to see the final sort of the steady state velocity profile quite nicely. So here time equals 3, so then you have a nice parabola, and it's fairly stable for the last time steps here. So this is a very quick way to achieve a solution for quite complex, actually, partial differential equations. One thing, they like to do it like this. Here you have your main script is a function. Matlab likes to do that. It's compact, and then you can write your script with the sum functions inside one single file. Yes, you can do that. But if you want to use this one, say in a connection with another program, or you want to debug it. Sadly here, after you have run the program, he doesn't remember anything. So the memory is cleared. So you can't really start debugging the script by looking at what's my different variables now. He has forgotten everything. So if you want to develop programs written like this, everything is function. You only need one M file that can then include many sub-functions, even nested, that's okay. But then he doesn't remember anything. So I won't recommend it. So what you do, you just remove the first part here, first sentence, like that. But now these functions has to be stored in separate files. So yes, you can do that. Yeah, shouldn't take too long actually, so we can do it. Let's try it. So I copy this one, new function, and we save him as this name, that's okay. And so we continue taking the next function, cut it out, new script, save, initial condition name, and then the last one, that's the boundary conditions, cut it out, new, and save. So now I have four separate files. This now is only the main program, but now it's ordinary Matlab main script. So he should run just as nicely, no problem there, except he doesn't have the clear all, close all CLC commands. I like those. Then you get the figures in front every time, so I prefer that one actually. So yes, now he works, and now also you have your solution in memory. So it's much easier to debug a program, finding the error, forming the program the way you want. Then afterwards, then you could of course have reinstalled this function sentence and then put all the functions inside one single file if you wanted to. But you shouldn't program it like this, it's hard to debug. So if we now go back to our script, I copy this one and paste it here inside my pdepe, my Poisson flow solver, the first one. He solves it from wall to wall, so that should be okay. So now, after he has done it, here I then call my solution, and then with hold on I want to plot not the surface, remove this one, I just want the final solution into the same plot. So I think this one should be correct. Let's try it. Now that's end time equals 2. That's not true, is it? No. What do we have? We have maximum time. That's what we are using. So let's take T maximum here. Let's see what happens. Something very wrong happened. I think we have to flip him. Let's see. We have to plot him the other way around. U first and then X afterwards. So you see they agree quite nicely. So that is another option for you guys if you want to have a solution just to compare with. You can find one from this toolbox in Matlab. How he has done it, I don't know. If you want to find out, you can investigate here. You can read about this script, and you have some references and tips about them. And if you're lucky, sometimes they provide you with the actual source code. So here, I mean, the function is called pdepe. So if we want to try it, if it exists, you write here edit pdepe. No, that was wrong. pdepe. Here you have at least parts of this script function pdepe, and then you can start reading how have they programmed this one. But here typically you will run into something you don't have access to. They will call a function that is not a Matlab script, it's a DLL or it's a MEX file, meaning they have compiled it to speed up the calculation. So it's not necessarily that you can find everything. But if you want to have a look at some advanced Matlab programming, you can edit or actually have a peek into these files. Okay, that was the entire solution. So now I want to take a copy here. I don't need this cosmetics. I want that one. I copy this one into the other I created. That was just half of the problem. It was a half here. And then I do the same here. Insert the same solver. So I want to compare with this one now. And, well, again, we should give him another name. Poissy half pdepe. Like that. Now I have to change the setup for this function pdepe. He was originally now taken to be from -1 to +1. Now he's going from 0 to 1. And I have to change the boundary condition as well. So here is now the boundary condition. The first one should be the same. Now the second one should be derivative equal to 0. How do we do that? Well, we can have a peek of the help file. They had an example somewhere. Let's see here. The first example that we copied. Look at the boundary condition. At 0 they have 0, that's okay. But the other boundary condition, here you have something changing with time, and then you have a derivative also changing with time. Well, actually for all time then, but so here you have what we call a Robin condition. You have a mix, a constant plus a derivative. So they're quite rare. I haven't seen it in practice before, actually. Well, I've seen it, but sort of obscure academic equations. But you have an example here. We want just a derivative part here of this one. So how do we implement that one? Well, further down here, you have the boundary condition, BC. First one was the one we have used already, and then you see the other one. You need a coefficient 1 for the Q. That will be the derivative. And then they have the constant in addition, which we don't have. So to obtain a Neumann condition, the only thing that we have to do here is then actually, I think it was the way we did it, yes. we change here. This one is not present, but this one is. Let's save that one and see what happens. Now I have the time to Tmax, and here I had Tmax to be 3. Let's stop at 1/2 here as well. I have the pause button. Remove that one. Again, we have to flip something, I think. Yeah, we have to switch the boundary conditions, I think. It should be the other way around. This one is 0. This one is u right. This one is 1, and this one should be 0. That was a little bit better. Still, we missed something. I don't really believe that solution. Again, I guess the axis, the distance here is not correct. Yeah, he goes from -1 to 1. That's not true. He goes from 0 to 1. Let's see if that helps. That's more like it. That's more like it. So yes, you can also use Neumann condition with these this pdepe tool. Quite straightforward. Always nice to have a correct answer in the background when you are dealing with numerics. And also here, if you have a nasty problem, you are starting to programming it, you make your own numerical schemes, and you are thinking, can this be correct or not? Dangerous. Then you can have a peek down here. Maybe your equation is even worse. You can't really describe it correctly with this one. Okay, but simplify your own equation to something that he can handle, and then you at least have something to compare with parts of your problem, to see at least you have done that part correctly before you then continue to expand. Maybe if you have a time derivative here, and then you have an x derivative, and then also you have a y derivative, for instance, a 2D problem and time. Then you can't use this, of course, but okay, reduce your problem to 1D, and then you have here something to compare with. Fairly easy. Okay, any questions from you guys? No? Then next time we are going to skip these diffusion equations and then look at another physical quantity, more transport, the advection equation, and then also look at that one hyperbolic equation in 2 dimensions, looking at surface waves and things like that. But that will be then the next time. Again, if you have questions, if there is something that you have found difficult, you want to repeat, you want to have more detail about, or something that you want me to address, send me a mail. Give me a call, something in advance, then I can prepare if necessary. Okay, then we stop here.